your professors seem caught off guard at all. Is that a pretty fair summary of everything?
Not even close.
Yeah. It's not a whole lot better for my children on school. It's also in the large scheme of things, it's not the most important thing. But I have a son in middle school, a son in high school, and then a daughter in elementary school. And the middle school and high school seem to have taken the dean's position that now that we have spent time investing into teams, there never needs to be a snow day again. So they're both just shifting to online today, whereas my daughter actually has the day off. And so it's the added fun of having two children at home who are going to school and another one making sure she walks around them saying, hey, has anyone seen my Nintendo Switch? I need to play some more video games today. So, that's always great. Plus, I don't know, I guess as a teacher, I should be happy that we've gotten to a way where we can do school from while there's snow. But I feel like my children, like snow days every now and then, are a fundamental right of kids up to a certain age. And so I feel somehow that I have stolen some of their, like as a society, I've stolen some of their innocence by they woke up and saw this big blanket of snow and a message that said it's a snow day on their phone, comma, so log into Teams at the same time you would normally show up to school. It's like, oh man, I almost want to just write them a note saying my children need to actually pretend like they're human beings, so they will not be attending school today. They will be making snow angels and throwing snowballs at themselves like a good-natured American child should. But I know that doesn't apply to you guys because you guys are all excited about coming to my class and were really scared when you saw the snow and we're like, oh my gosh, I hope that doesn't mean we're canceled. Don't worry, it doesn't. Rain or shine, I will make sure you always get your daily dose of statistics. So you don't have to worry about that. I got you covered. Okay. Today we are back on track with lesson 7, random variables. Hopefully you guys look through the guided lesson. I do think it is funny. I put that book up there because that was a book my advisor actually had. It turns out like getting truly random numbers is very difficult to generate. So they actually, especially before there was widespread computers, they had this book that is just a book of a million random numbers. So that if you needed a random number, you could open the book and there is a truly random number. And what's funny is they still sell this book on Amazon, and these are actual book reviews of the book, which I find more entertaining than the book themselves, especially the last one, which I'm really hoping the guy thinks he's being funny because otherwise he has some issues that he needs to work through. Before we get into today's stuff on random variables, I wanted to make sure we focused on today we've got homeworks 4 and 5 in lab 2 are due 1700 today. So if anyone has any questions on either of those, I want to make sure that you feel comfortable about it after class. If not, I'll be free after class for most of the rest of the day if you have any follow-up questions on that, but I want to make sure you guys feel good on that. And then also, quiz 1 is not due today, but it is open today. So as of 0700 this morning, the first quiz is open. I put up a post kind of explaining how to go through that. But basically, you can start taking it anytime from now until 1700 tomorrow. But once you choose to start it, then you have to finish it. You get 20 minutes. Shouldn't need all 20 minutes. It should be, it's a shorter quiz than that. But you log on to Blackboard with it. And if you have any questions, let me know sooner rather than later, because if there's a problem, we can deal with it now. But if there's a problem and you tell me at 1701 tomorrow, I'm going to be less sympathetic to your cause. Okay, so with that in mind, does anyone have? Yeah.
Is the quiz? It's open open book.
It's open. It's open. Absolutely. Thank you for interrupting me. Like I said, that's what I needed you guys to do because I didn't know anything. It is open. Everything except other people. So you can use pretty much any resource except other people or sites that represent other people, like, Chegg or Course Hero, but basically any static source of information, whether it be your notes, my slides, your code, my explanations, my code, all of that is fair game on that. That said, a question that came up both the other two lessons, which I just realized, I am recording. Hey, look at me, I actually learned. I mentioned the other two classes. People asked, will we have to write code for the quiz? In general, for quizzes and GRs in the final, there will be times where you are expected to use R. But on this first quiz, A, we haven't done a lot of stuff that requires R. And B, even when I require you to use R, even if it's something later, I will almost always only require you to do like a single line of something in R. Nothing should require you to write a program or a block of code or something to the extent of what you would do in a lab, right? I might have something where it's a block of code from R is in the exam, and it says, here is a block of code and the output, what does this mean? And there's like, A, B, C, and you have to interpret it. But the questions are not designed for you to have to do, hard work. It's kind of akin to on a calculus test, if you're expected to use your calculator, it's to, figure out the computation part with a couple of lines. Same thing here. If I ask you to do something in R, it should be a one-line computation that doesn't require you to be able to write elegant code on the fly. It just requires you to understand, for example, in a couple of lessons, we're going to be talking about a particular distribution, like the binomial distribution. And so you will have to know, for when we're doing something like that, that if I were to ask you, hey, what's the probability if I flip a coin this many times that I get 3 heads, you'd have to say, well, I recognize that's a binomial distribution. And then you'd have to know that in R, you could go P binom and then the numbers and the probability, but it'd just be a single line and know it. But since it's open code or open everything, you can look that back up if you want, or what a lot of people do is they just keep their own private RMD file going throughout the semester called like test cheat sheet. And every time we learn something new, they just put an example line of like, here's an example of binomial code so that it works. And then later when the question comes up, they just have to go in and edit the numbers to the specific question and run it. So you don't have to write code on the fly. All right, that was a long answer to what should have been a simple question. Anyone else have anything that I can ramble on about? All right. And like I said, if you run into any questions later on the quiz, hit me up. If it's about technical things like you can't log into Blackboard or something like that, hit up the Blackboard people first. That email of Mary J. Blystone is the main person who will usually get it fixed right away. And if she or someone else is not responding in a quick manner, let me know, because I can't fix the problems, but I can lean on the problem or lean on the people who should fix the problem. So let me know soon. Don't just wait and later say, yeah, I never did the quiz because I couldn't get it in. That's dumb. There's few things that I can do where I can throw my rank around, but that's one of them. Okay. If anyone has any other questions they think of, feel free to interrupt me. We'll probably finish this early and you can bring it up again later. Or if while I am showing information here, interrupt me at any time. Again, I don't have my phone. I thought I did, but it's my calculator, and it turns out I can't log into Teams on this thing. So just interrupt me at any time. All right. Okay, so we're talking about random variables, and random variables are, there's a lot of specific things that we could do that. We're going to be dealing with random variables for pretty much the rest of the semester. So I'm going to talk about a few calculation things concerning random variables, but I really want to focus up front about just being clear about what a random variable is, because again, like so many things in this course, it's one of those things that is simultaneously not really difficult, but we have to be specific to understand our terminology so that then it pans out in our equations, because last semester I had people halfway or 3/4 of the way through the course and still couldn't really articulate well what a random variable is. I could tell that in their brain they understood what it was, but they wrote different things or unclear things on a piece of paper, which I had a few arguments with them. And I said, well, sir, but I know what it is. I just wrote this. And I said, awesome. I know you deserve an A, but I'm just going to write down a B, right? Okay. Oh, so what you write is important, right? So be clear about what you write. So a random variable, we usually represent it as the capital letter, like capital X, like, right? That's like the random variable X. And it can have specific values represented with lowercase letters like little x. Okay, so that's a little confusing, but the idea is that let's say I roll a dice, right? So let's say I roll a dice and I say the random variable x equals the number on the die, right? Excuse my horrible handwriting. I'm trying to lean over and write on this, right? And so x is a random variable. X can equal 1, 2, 3, 4, 5, and 6, right? So each of those are examples of specific values that it can be, right? So X is the random variable, and little x are the specific values that it could equal. It sounds like a weird, like unnecessary distinction, but the reason that I make that is to kind of help understand the difference between a random variable and a variable, right? Because you guys have dealt with variables all throughout USOF and high school and algebra, and probably even before then, right? And so, like, when you had equations that were things like y equals x cubed plus 5, right? Y and x there are variables, right? But they're variables in the sense that they can change. You don't know what they are. But once you know everything about the problem, you know what they are. You just don't know now, right? If I told you that x is 2, well, then you know that y has to be 13, right? Because once I give you all the information about the problem, you can then tell me what the variables equal, right? Random variables by definition are different, right? In this case with the rolling the dice, I can say, hey, I am going to x, the random variable capital X is the number that shows up on the die. And I can tell you that it is the possible size of the die are 1 through 6, and that it is a fair dice. So each one of them has an equal probability. But then that's all the information, but if I roll it and then put my hand over it and say, now tell me what x equals, you can't tell me, right? Because it is by definition a random variable. The only thing you can tell me about it is you can tell me what the probability of it being equal a specific value is. So you can never tell me x definitely equals this. You can just say the probability that x equals 1 is 1/6. The probability that x equals 6 is 1/6, right? So a random variable is something that is random, right? That it is, I know I can define it in terms of probability, but that's the most I can define it. Over here, with this type of variable, if I define x, then I fully define y. Here, no matter what I do, the best I can do is tell you the probability that the random variable will be equal to different things. All right, that was a little bit rambling on there. Any questions on that distinction of what a random variable is?
Yes, sir.
Yeah.
So a specific variable could have like a normal XY graph, and you could just find a point and that gives you all the information. But like a random variable couldn't have that. It would have to have like a chart of probabilities.
Right. Yeah, exactly. I have a chart of probability. So like on the right-hand side, I could say, y depends on x. And so whatever x is, y has to be another thing. Whereas a random variable, I can say, here is the probability distribution of x, but then whether or not x equals certain values is random based on the probability. You might have a higher probability. Like if I have a weighted dice over here and I say, hey, 6 actually, there's a 0.5 chance of it being a 6, and so this is an unfair dice, there's a higher probability that X is equal to 6 than the other numbers, but I still can't tell you for sure what it's going to be. I can only tell you what its probability distribution is. And we'll get into a little bit more of what we can, ways we can describe it, and we can describe attributes of X, and we can give statistics about X, but in the end, it is still a random variable that every time I look at it, or every time I roll a dice, or every time I flip the coin, I can't tell for certain what it's going to be, only that it has a probability of being certain things. Okay? Does that answer your question, or did I miss the meaning of it?
No, sir, you got it.
Okay, cool beans. All right. So I can then say, I can talk about what kind of random variable is. So for right now, I'm going to focus on discrete random variables. We'll talk about continuous later. But if X is a discrete random variable, then that means there are a countable number of specific values it can be, right? Back in the case of our dice, that is a discrete random variable because the specific values it can take on are 1, 2, 3, 4, 5, 6. And so there is a countable number of values. It's not like saying, I don't want to get too far into continuous, but I could say, hey, I'm going to start a timer and then at some random point just stop it, right? Well, that is, it could be any, even if I say I'm going to stop it before 5 minutes, it could be any time between 0 and 5 minutes. It's a infinite uncountable amount because no matter what 2 times you pick, there's another time it could have been in between, right? So a discrete means it is a countable number of values. And I know it sounds kind of weird that I'm saying countable when some people want to say, well, why don't you just say there's a finite number of values, like on the dice, there's 6 things it can be. The problem is, and I don't want to harp too much on this, is that you can have an infinite discrete random variable. So picture a theoretical imaginary dice that has an infinite number of sides that go from 1, 2, 3, 4, 5, and just keep going forever, right? That is a discrete random variable because it is countable. I can put them all in order. I can say there's 2 and 3, and there's no option between 2 and 3. And so I can count them all in order, and I can assign them a probability, right? Because if I said, hey, the probability of rolling a 1 is 1/2, and the probability of rolling a 2 is 1/4, and the probability of rolling a 3 is 1/8. You guys know that I can go on for infinity, but that sum converges to 1, right? So it is a valid probability distribution that is discrete, even though there is an infinite number of values that it can take on. So a discrete random variable just means that it is a countable number of values that it can take on. That's not the biggest point I want to make today, but are there any questions on how that works out? Okay. The way we talk about the probability that X has a specific value is probability that X equals X, right? So if I, in my die option, if I say, what's the probability that X equals 3? Well, that is 1/6 because the random variable is X. I can't tell you what it is, but I can say that the probability that X equals 3 is 1/6, right? Now, one person in the last class asked, well, why do we write it in there with that little x? Like, does little x have any meaning, or should we just always give it a number? The reason we do that is twofold. One, that's to kind of generally give to show it as a concept, but it also could be helpful because in this case, I just know what that the probability of each number is 1/6. But we're going to get to larger distributions where maybe the probability is represented by a function. And so in that case, I might want to say, you know, f of x equals probability that the random variable x equals little x. So in that case, I need this second part to say, hey, this function of x is, I put in some value of x, and then the function spits back the probability that the random variable capital X equals that little x. So that's why we have this weird form here, but we usually are talking about specifics like this. Not only are we usually talking about specifics like that, usually we use shorthand because a lot of times I'm only talking about the random variable X. So if I'm just talking about rolling a die, and I know that every time I talk about probabilities, I know that I'm saying the probability that the random variable X equals 3, I will shorthand this as probability of 3, equals 1/6. So be aware that this is the kind of technical long way of making sure that we know which random variable we're talking about and what it equals. But if we're in a problem or a scenario where we're talking about the same problem and we all know the context, you can just shorthand it to what's the probability of 3. And it's assumed that we're talking, what's the probability that the random variable we're talking about equals to 3. Any questions about that? All right, one thing that is understood in all of this is that the random variable has to be a number, right? So X equals a number that I can do things with, because we're going to be able to do some calculations on it. Because we want to say I can talk about the value, like we said, the value that it takes on depends on the probability distribution. We already kind of talked about that. And to use an example, I made up this example of randomly selecting an Air Force officer. I say made it up, but this is actually based, I did this last year, and it's using real numbers from the size of our forces in 2019. So I'm going to first define my random variable, right? And so I'm going to say, let the random variable, capital G, be a random variable that represents an officer's grade, right? So your grade is 01, 02, 03, all the way up to 010 if you're a 4-star general. So I've defined my random variable saying it is a G represents the number of a random officer's grade. So that's like I'm taking everyone in the entire Air Force, putting their name and rank, or all the officers, their name and rank in a big hat, and then pulling one out at random, and whatever the number equals is what G equals to. So that's what G is. So G can be equal to anything from 1 to 10, but I don't know what it's going to be equal to, okay? It can take on specific values, G, right? And so like we said, officer grades go from 1 to 10 if we ignore the prior enlisted like E ranks. And it is discrete because it takes on just a countably, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's not an infinite number of ranks in between that are uncountable. And so this is a discrete random variable because it has a discrete countable number of possible values that the random variable can take on. Everyone with me so far? Any questions on the setup? Okay. So now I can come up with a probability distribution that says I can't tell you what G equals because every time I look at G, it's going to be something different. G, if I pull out a thing, G could equal 2. Then I put it back. Then I pull out something else. Now G equals 5 because it's whatever the randomly selected officer's rank is. But I can tell you what is the probability that the random variable G equals one of those specific values, right? By doing the probability distribution. So I made this probability distribution by looking at the breakdown from the Office of Personnel Management of how many officers we had in each rank at a particular time, and then figured out the proportions or the probabilities of this situation. So in this case, my population is all officers, and I had all of the information about the entire population. So now I can give you this probability distribution. So this is G. This is all of the specific values that the random variable can take on. And then I say this is the probability that the random variable G equals that specific value. So the probability that the random variable G equals the specific value 1 is 0.126. That means that about 12.6% of the officers in the Air Force are second lieutenants, right? And I can do that distribution for everyone on there. So I can't tell you what G equals. When I pull it out, I can't tell you what it's going to be, but I can tell you what the probability that it will be equal to a certain number that represents the rank. Like I said, none of this is super difficult to understand, but it is important to understand the terms here of what the random variable is, what the probability, what the distribution, what the specific values are. So with that in mind, is there any questions on anything that you are seeing on the screen here that needs further clarification, or any questions you have about something I've said or what you see here?
We would be given the officer distribution, right? The probability distribution.
Yeah, I mean, it depends on the type of question that I asked. If I were to ask you, hey, what is the probability that G equals 5? Then yeah, I would have to give you the probability distribution, or at least the part of it that equals 5, for you to be able to answer that exactly. I could, there's different ways of doing it. I could give you everything except that and still ask you the same question, and you could figure it out, because you know that, hey, this represents all the possibilities. Therefore, the probabilities add up to 1. So the probability of it being 5 has to be whatever is 1 minus all the other ones. As we get into the next slide, you'll see that there are other questions I can ask with the probability distribution. Or I could ask you, if I said, what is, I'm trying to think of something I can give you without the distribution. I could give you just this setup, right? And then ask you conceptual questions of, maybe and say, what does capital G represent in this situation, and have a multiple choice. And you'd have to recognize that it represents the random variable. Or if I said, what does, the value of 5 represent, and maybe give you a multiple choice, and you have to say that it represents a specific value of the random variable, but not the random variable itself. So yes, I would have to give you some form of the distribution to calculate exact numbers, but I could also reverse it, where I gave you other things and then ask, multiple choice conceptual questions that required an understanding of the relationship and definition of a random variable, but not the actual calculation, if that makes sense. Does that answer your question?
Yes, thank you.
Awesome. Okay. And then I'm watching the time, but if I go long, someone tell me, because my other 2 classes ended on the hour, but you guys do not. You guys end, what time do we end at? 43, I think. So I gotta remember that we're ending at a random time, so don't let me go past that. Okay.
38, sir.
38. Oh, even better. See, that's why you got to keep track of me. I can do high-level statistics, but not simply adding 53 minutes to 11:45. Okay, so let's hold on to this distribution for a second to use it as an example. And so let's talk about some of the things that I can tell you about the random variable. So I already said I can't tell you, if I say here's the explanation of the random variable G, I can't tell you G equals blank. I can tell you what's the probability that G will equal certain things, but there are certain aspects of G that I can tell you. And one of those is the expected value, right? So when we talk about the expected value of a variable, we either write it out and say, hey, the expected value of the random variable X, or we write it as E of X there, which means the same thing, or we write it as mu. That's what that last little Greek letter is. All of those mean the same thing. We also could call it the mean of the random variable. Now, this is where it gets a little confusing, but it's not bad. I want to make sure I clarify it. Before, we used to say, when you were in calc or algebra and someone said, hey, you've got 1, 2, and 3. And if they said, hey, what's the mean of those numbers? You just said, oh, well, it's 1 plus 2 plus 3 divided by 3, and that equals 2, right? And that's not wrong. It's just making some assumptions. And that's something I always try to, people always, when I was teaching high school, I had some students who were like, oh man, you've done college or, grad school math, math must get really hard as you get higher and difficult. And you guys are far enough along in your courses that if you stop and think about it, it's not that things really get more difficult. They just get more specific, right? Like in physics, you learn, hey, here is the equation for your current velocity. And then you go into the next class, like, oh, well, later you should really add into the equation. You should, that's assuming you started from rest. Now let's assume that you might be starting at any speed, so we got to include your initial velocity. Then you get later in class, like, well, that's assuming there's no wind resistance, so here's how you add wind resistance. That's assuming that relativity isn't taking into account. But if you're going really fast in space, then you need to take into account. So here's how you add that stuff in. So nothing was wrong. It was just getting more and more specific, because early on you just made a lot of assumptions. And so in this equation here, this is an expected value, but it's an expected value that assumes that you have an equal probability of choosing 1, 2, or 3, right? Because we never wrote it out, but implicitly implied here was that you're saying, hey, there is a 1/3 chance of getting a 1 plus a 1/3 chance of getting a 2 plus a 1/3 chance of getting a 3. And you get the same answer, right? Because those are the same two equations. It's just that we factored out the 1/3 and then just put it on the bottom in that top equation, right? And so that's what that top equation is it is when you calculated the mean before, usually people just taught it to you as, hey, you add up all the numbers and divide how many you have. Really, what you're doing there is when you divide by how many you have, what you're really saying is they all have the equal probability. So dividing by that number is the same as saying the probability in this case is 1/3 and adding up each one, right? We are now to the point where we can now say, hey, it's possible that you might not have the same chance of getting each one of those, right? Because this was basically an example of a random variable over here. You're saying, hey, if I have 1, 2, and 3, what's the mean or average or expected value of those, assuming they all have equal probability? Now we have enough tools that we can say, well, what if in that situation I still have 1, 2, and 3, right? But what if there was actually a 50% chance of choosing 1 and only a 25% chance of picking 2 or 3, right? That they had a lower probability. Well, I can do it the same way we did on the left here. It's just now I have different probabilities. So now I can't just use this version. I have to use this version and say there is a 0.5 chance of getting a 1 plus a 0.25 chance of getting a 2 plus a 0.25 chance of getting a 3. And this is then going to be 0.5 plus 0.5 plus 0.75, which equals 1.75, right? And so that is less than what we got before, but it makes sense from a common sense standpoint because there is a bigger chance of me getting a 1, and so it makes sense that my expected value is closer to 1 than it was over here. And the important thing the last important thing to understand about it is that does not mean that I expect that if I have 1, 2, and 3 as options, that I am expecting that my answer will come up as 1.75. That's not even one of the options, right? It's one. My options are 1, 2, and 3. That 1.75 there is saying if these are the probability of getting each of these numbers, if I keep looking at the random variable X over and over again, and I look at it and go, okay, I got a 1. And I look at it again, oh, I got a 1. And then I look at it again, oh, I got a 2. I say looking at it, we can think of it as a dice that's weighted that has a 0.5 chance of one and a 0.25 chance of the other. And every time I get a new random value for it, I write it down. The average of all of those values are going to converge to this 1.75, right? When it makes sense, that's close to 1 because I'm going to, based on the probabilities, I'm expecting to get 1 more often than the other ones. Over here on the left, the expected value is 2 because I have an equal chance of each one of those. And so I am expecting to get 1, 2, and 3 the same amount of times. And so when I add them all up and take the average, I just get this value here. So again, it's not that we were doing it wrong before. It's just before we were assuming that they all had the same probability. If we do it, if they do all have the same probability, we still get the right answer. Now we just have the method to deal with a different probability distribution. All right, there's a lot of stuff scribbled on my screen. Does anyone have any questions before I delete it and move on to some of the math?
This might be a kind of stupid side question, but is this the same way that they calculated if you have like 3 random doors and you pick a door and then they eliminate one door, you have a higher probability of getting it right if you switch your answer?
Yes, so that is called the Monty Hall problem. And that is, if you want to calculate why that works, it is based on conditional probability, but it does still come to the fact that you have a different probability distribution. To give a real simple way of doing it, it's saying, hey, if I have 3 doors, and let's even make it 4 doors, or shoot, we can make it 5 doors, right? And so if I told you, hey, there's $1 million behind one of these doors, then and that's all the information you have, then you could pick one of the doors and you would have a 1 in 5 chance of winning the prize, right? But the Monty Hall problem is basically saying, hey, okay, there's 3 options here, and if you pick one, then you have a 1/3 chance, right? If I then say, if you said, hey, this is my option, and then I say, hey, the money is not in this one, and I ask, do you want to change your answer? You might say, well, I still have a 50-50 chance because, and so I don't want to change it. But if anyone's interested, I will go into the specifics of it. You always want to change your answer because basically by changing that, your answer, how can I do this in a real short version? There is a nope. You know what? Without having it prepped up, I'm not going to have a pretty way. The video that's on the guided lesson gives a pretty good explanation. But if someone is interested, I think it's a really cool proof. I will definitely go through it with you, but I don't want to spend time in class. But the short version of your answer is yes, it does have to do with expected values of basically saying the expected value of your current door is less than the expected value if you change, and therefore you should change. Which doesn't make common sense, but it makes math sense. All right, any other questions on all the stuff that I erased? Okay. So it is, we can think of it as a weighted average, right? Back in the day, we just talked about the average, which we just assumed they were all even. Now we're saying, hey, it's a weighted average because some things are more probable. Some specific values are more probable than others. And the equation is this, which we saw executed. This is just the fancy math way of saying it, is that saying for every possible outcome, take the value of that outcome and multiply it by the probability of getting that outcome, and then add all of those up, right? We saw that with the 1, 2, 3, where we said take 1 times the probability of getting 1 plus 2 times the probability of getting 2 plus 3 times the probability of getting 3. That's how we calculate the expected value. Any questions on how that equation works? All right. Now, the problem with expected value is it is a great it's a thing that is a number, right? Because I can just say the expected value of x is a number, unlike the x itself or a random variable that I can never tell you. I can tell you exactly what the expected value is. Like, for example, if I had a 3-sided die, which is a thing, I have some if you guys want me to find it, but if I had a 3-sided die and I said one side was 999 and one side was 1,000 and one side was 1,001, and I said they all have an equal probability of being rolled up, I could add them all up and divide by 3, and I would get that the expected value is 1,000. Sorry about my writing there. If I had a different die that had was three-sided, and one side was a 1, and one side was a 1,000, and one side was a 1,999, I could do the same calculation, and I get that expected value is 1,000 again. And so that is good. That tells me that, hey, the expectation over the long run of this is to get 1,000. These two dice are obviously very different, right? Because although they have the same expected value, they are much more spread out. If I'm using this dice to play Monopoly, first of all, it's going to be a very long game of everyone going around the board. But on the first die, I know that on average I'm going to get 1,000, but that at worst I'm going to get 999, and at best I'm going to get 1,001. Whereas on the other one, it's the same expected value, but I could get anywhere from 1 to 1,999, right? So expected value isn't the entire story. I need some measure of how spread out the data is, and that's where variance comes in. So the variance of X, which we say as the variance of X, the random variable, or as var X, or as this right here is sigma squared, because it turns out variance is the square of something called standard deviation. And since it's related so much that they never came up with an actual variable for variance, they just call it sigma squared. So we only have so many letters that we can use as mathematicians, so we try not to waste them when we can. And so it is a measure of how spread out the data is, right? So, and it's a measure of how spread out it is from the expected value. So in my dice example, that first die would have an expected value of 1,000, but a very small variance because all of the possible outcomes are very close to the expected value. Whereas the other one would have a much larger variance because the numbers are spread out quite a bit from that expected value. So in addition to being a measure of variance, this tells us that in order to calculate variance, we have to first calculate the expected value because the variance is a measure of how spread out it is from that expected value. And so the way we do it is with this equation that looks a little complicated at first, but it actually makes a lot of sense if you read it and see what's going on, right? So it is very similar to the first one. It's just instead of X up here, we have this whole part here, right? Other than that, they're exactly the same. This part right here, if you look at it, mu is the expected value. That's the thing we calculated up here, right? So X minus mu, that's saying for every possible little x, every possible outcome, figure out how far away it is from the expected value, right? That's what X minus mu is. The squared part is just saying sometimes it's going to be less than mu, sometimes it's going to be greater, so I'll get a negative or positive. So square it so I don't have to worry about it, right? And so now that circled part on the bottom is how far, I'm taking how far, a measure of how far each possibility is from the mean, and then I'm multiplying it by the probability of being that far away, right? So if I use the example of rolling a dice, the possibilities of rolling a dice are 1, 2, 3, 4, 5, and 6. And you guys can take my word on it. The expected value of rolling a dice is 3.5, assuming it's a fair dice and there's a 1/6 chance of getting everything on the dice. And so to calculate the variance for every possible outcome that I have here of 1, 2, 3, 4, 5, 6, I would say, how far is 1 from that? Well, 1 minus 3.5 is negative 2.5. And then I would square it so I don't have to worry about the negative, and I would do that for each thing, right? So I get this measure of how spread out things are, because if it's very far away from the mean, this number is big. And then I say, what's the probability of being that far away? So it takes how far away I am and then times the probability. And so if a lot of things, if there is a high probability of getting things that are far away, then my variance is going to be very big. If there's, just one thing that is far away, but it is very far away and it is a low probability, then it might still affect the variance. But overall, I get this calculation that is weight. It's a in the same way the expected value is a weighted average. The variance is a weighted average of how far away my values are from the mean. And so that the bigger the number is, the more spread out they are, the smaller it is, the more clustered they are around the mean. So any questions on the concept of how variance works and what it's measuring? And then I can go through a specific example in the time we have left. But any questions on what it means and the concept of it? Okay, so let's look at this in the example of our randomly selected Air Force officer. So if I wanted to find the expected value of this random variable, then like we said up in this equation right here, it would be for every possible outcome, 1, 2, 3, and so on, I would take that outcome times the probability of getting that outcome, plus the next outcome times the probability of getting that outcome. And I would do that all the way through, right? And I can grab all those numbers from up there, and I get this answer 3.33, right? Anyone want to give a stab? I'm not expecting full answers at this point, but everyone think they can explain what does the number 3.33 mean in this situation? And remember, I can't see hands, so just start talking if you think you got an idea.
They'll probably be a captain.
So yes and no, right? So and that's why I asked, because you're right. So 3 would represent a captain, but remember that 3.33. And I appreciate that you said they'll probably be a captain. You didn't say, like I've had answers before where people said, they're 1/3 of their way between being a captain and major. We don't know anything about that, right? Because every time I look at someone, I only can see their number. So what that really represents is that if I take all of the, because there's no such thing as a fraction of an officer, right? Like I said in my last section, it's true that in the last 20 years, I've worked with some people who I would consider fractions of officers, but mathematically speaking, that's not a real thing, right? And so what this number means is if I keep taking out names, look at the grade, write it down, do it again over and over and over again, that overall, if I take all those and average them out, then it's going to get to 3.3. Now, you could make some conclusions about that, but you can't know anything for sure, right? So it's fair to say that you might say, hey, on average, I probably have more captains, right? Because that is close to 3. And so it seems like on average, you have that captains, it would make sense that if captain had a higher probability, that you would expect the expected value to be closer to 3. That being said, if I didn't give you this distribution up here, and I just said, hey, the expected value of G equals 3.33, you can't know for sure that's what it means, right? Because mathematically speaking, obviously this would be a stupid Air Force, but I could have an Air Force where there were only second lieutenants and only 4-star generals, right? But if there was just the right number of second lieutenants and just the right number of 4-star generals, so the probability of a second lieutenant was higher and a general was low enough, but it pulled it in there, the expected value would be somewhere in between them, and it could be 3.33. So the expected value of 3.33 doesn't mean that most of them are captains. It just means that the distribution is such that my in the long run expectation is 3.33, right? Now, obviously you can use common sense to say that's probably not the case. And then it probably means that I've got more officers in middle to low grade than higher. But that's why that's why the variance is an important additional statistic that helps us make better and clearer conclusions. Because now that I have the expected value, I could calculate the variance. Or maybe I'm in a situation where I just gave you the expected value and the variance. But if I calculate the variance here, which I do by for every single possibility, I then figure out how far it is from the mean that I already calculated, and then square that, and then multiply it by the probability of that happening, and I do it every single time and add that all up, I get this variance of 0.23. And since that is a relatively low variance, we can talk later about how I know that's low, because it depends on what kind of numbers we're talking about, whether or not it's big or small. Since that is a low variance, then that means that I am that this is not spread out that much. So most of the data is going to be close to the expected value. So now I can make the statement that he made before, saying that with both this being the expected value and this down here being the variance, I can now say it seems that most of our officers are are closely clustered around captain, which means most of my officers are probably first lieutenants, captains, and majors. And sure enough, if I look at the probabilities up here, they account for about 70% of all of the officers in the Air Force. And so that's why expected value and variance are both give you certain information by themselves, but together they give you a better understanding of the distribution. And if we have the distribution, then it's even better, because by looking at this distribution, I can see, oh yeah, it is centered around captains, and then it is heavily right skewed as it trails off to our 4-star generals. And I can see from down here that my statistics back that up, because sometimes I have the distribution, sometimes I only have the expected value, sometimes the variance, sometimes I have both. And so the important part is understanding how they all interact. So depending on what pieces of data I do give you, or you are given, what other things you can be sure about versus make conclusions or assumptions about. All right, I think we are at about 2 or 3 minutes left. Any questions or clarifications on what's on screen or what I was writing here? And I will do my best to answer them. And if anything else, I will hold on to either answer after class or in Thursday. So what do you guys got?
Sir, just to clarify, the basically EG kind of represents the direction from the median of G. So
what does? I'm sorry, what does?
So like if we're looking at the G values of 1 through 10,
Yep.
EG kind of like represents the direction. So if we said like 5 to 6 was the center, then it would direct us to which like side the information's based on.
And so the expected value is, if I were to take infinite draws of this samples of this random variable, that's the expected value is where I expect it to average out in the long term. So it's exactly. It's where I in this case, the expected value is 3.33. So that tells me that it is the distribution is, I realize I'm restating what you said, that it's centered at 3.33, and whether that means it is heavy on the low side and is right skewed, or if it is, centered exactly at 3.3 and it goes down to the negatives and higher, it depends on the additional information I have. But 3.33 is its center of mass, for lack of a better term.
Okay.
Because exactly. I was going to rephrase it again, but you said it well. I don't need to just say it for the sake of me feeling like I'm smart. Okay, so I am going to stop it there because I don't want to keep you guys longer. I will stay off here. I will stay on here for a couple more minutes if anyone has any lingering questions and the time to answer them. But otherwise, focus on getting the lab and the homework done and turned in today. Make sure that you either do the quiz or talk to me about what problems you're having before 1700 tomorrow, because I'm not going to see you guys again until Thursday, and make sure you knock that out. And then otherwise, I'm free today and tomorrow if you got any AI. And otherwise, go make some snow angels before Thursday, and I will see you guys on Thursday, if not earlier than that.